Okay.
All right, so hi everybody. Thanks for joining us for this Victor short class session. So today we have the pleasure to welcome Grace Battle. She's a researcher at the NASA Jet Propulsion Lab in California, and she's going to show us an overview of some remote sensing tools and data that we can use on Victor, and basically, open that for questions in the end. If you guys have any questions or if you want to comment on anything, we should have some time at the end of the session for that. All right, so as usual, if you have any questions during the presentation and the activities, you can either raise your hand or write on the chat as you want, and I can monitor that for you, Grace, so you don't have to monitor that, and I can tell you if there's a question.
Okay, perfect. So does this terminate after an hour exactly, or it's okay? So it will shut
It's
down
about an hour,
for us,
yeah.
But it will not automatically turn us.
No.
Okay, perfect. Yeah, it
All
happened
right.
to me last time. So,
no problem. Yeah, no, it can go on, yeah.
Yeah, so hi everyone. So I'm Grace, and as Sylvan mentioned earlier, I am at the Jet Propulsion Laboratory. I work as part of the Opera project. I am the validation lead for the two of our main products, the core-registered SLC and then the displacement product. Yeah, but in general, I'm a volcano enthusiast at heart, I would say, and yeah, my background is in volcano geodesy, remote sensing, and forecasting, developing forecasting strategies, in fact, using satellite data. So today I'll be walking you through on how we monitor volcanoes from space using remote sensing data sets, and more importantly, how we could translate these observations into information that can support your science curiosity or support your hazard monitoring and decision making if you're working in an observatory. So in volcanology, our overarching goal is obviously to move toward this efficient way of timely and accurate derivation of information to mitigate the societal impacts of geological hazards and the cascading effects. So we want to be able to detect anomalous behavior, monitor the unrest, forecast how the future state of the volcanic system will evolve, and eventually assess the different what-if scenarios that will impact our society. So why do we want to monitor volcanoes from space? Basically, there are roughly 1,200, 1,500 plus potentially active volcanoes worldwide. The Holocene volcanoes from the Smithsonian, I think it's around 1,250 volcanoes in their database. Many of these are located in remote geographic regions where ground-based monitoring is very limited or entirely absent. So this is where satellite observations could come in, could provide us a unique opportunity or advantage to monitor the volcanic systems consistently and safely without going there frequently. So it's a very essential component of our modern volcano monitoring practices. So here in this figure, I'm just showing this lava placement event at Ertalie using both Sentinel-1 and Sentinel-2 datasets. This is from the paper of Sebastian Balad 2019, showing all those different satellite imageries that were used to get information about this event. If we just step back a bit and try to understand what remote sensing is, remote sensing basically refers to observing, in this case, the Earth from a distance. We would typically distinguish between passive sensors, such as optical systems that rely on sunlight, and active sensors, for example, such as radar systems that generate their own signal. Um, Synthetic aperture radar, or SAR, we will go back to this later on, operates in the microwave domain and has this key advantage of being able to acquire data regardless of weather conditions or time of the day. So you can have images day or night, and it's particularly monitoring the volcanic systems that are often, you can see in this example, cloud covered environments. So we know that there is no single kind of data set that could tell us when the eruption could be and what is really happening beneath the ground. So this kind of like just slide illustrates that there is no single data that would give you a complete picture of the volcanic activity. Instead, we would want to rely on combination of complementary observations, including for sure ground-based observations. Here is just an illustration of how remote sensing techniques can be used during a hypothetical eruption cycle. This is from paper of Pyle et al. In 2013. So you have this seismic event, for example, that starts here, no seismicity, but you may have pre-eruptive deformation, you may have degassing already. And once you enter or transition to somehow more unrest period or co-eruptive phase, you can probably detect hotspot already from infrared signal, and you can have an escalation of your or inflation in your radar data or ground-based ground deformation measurements. And then as you go along the cycle or the eruption period, you can have information from other wavelengths of the electromagnetic spectrum. You can see ash from the visible range, IR, and you can see much more degassing in higher altitude, plume dispersal, and so on and so forth. But basically, this is how you would use remote sensing data. Normally, the deformation can see really, years before you have an eruption. For example, you can see that, for example, volcanoes are slowly inflating over time. So in connection to the previous slide, so this one shows us how different parts of that electromagnetic spectrum interacts with the atmosphere, basically. Before we go deeper into the specific data sets like thermal, INSAR, or IR data, it's important that we kind of ask this fundamental question of why do we even need these different types of sensors in the first place? And of course, the answer is that because all remote sensing systems, whether they are operating as optical or radar, are observing the Earth using different wavelengths of the electromagnetic energy. And each part of the spectrum interacts differently with the atmosphere and the Earth's surface. If you look at this figure, you'll notice that the atmosphere is not equally transparent across all wavelengths. So the transparent part are the white bands, if you can see in the figure. So in the visible and thermal infrared regions, which are used by optical sensors, the signal can be strongly affected by clouds, for example, and other atmospheric gases or even ash. And it's particularly important for volcanoes because eruptive environments are often dominated by exactly these conditions. You can have dense clouds, ash plumes, and aerosols. So optical systems may be limited once the activity started, for example, and can be even completely blind during critical periods of unrest or activity. So if we move towards the microwave signal here, for example, longer wavelengths, um, where radar actually operates, we enter a region where the atmosphere becomes much more transparent. You can see that part. And microwave signals basically just can penetrate clouds and even some vegetation, allowing us to observe the surface regardless of, again, what time of the day and what weather condition. Although if you have ash particles, it can interact or reflect back radar signals. So this is the main motivation of radar or the use of SAR data in volcano monitoring. We'll go through that later on, but yeah, so this is just a slide showing you why we need different sensors and how we use them to understand the volcanic system. So in terms of optical sensors, thermal anomaly, SO2, plume height measurements, this is a very good summary of like the different satellite sensors and their characteristics that are currently available, and what organizations are currently providing them, for example, or projects. So you have satellite sensors from MODIS, that has Aqua and Terra um, um, satellites with them. And then this one is Severi, it's a geostationary sensor. And you have Aura and Sentinel 5P that are accessible in many platforms or free platforms recently. So I will stop a bit because I thought we could have some sort of like demo and interaction if that's fine with everyone. But I think my entire goal here is not just present things and then you absorb the information, but also to have this, really hands-on experience on how you could utilize satellite data if you haven't had a chance to work on them recently. So I like the worldview or data nasa.gov platform because it just gives you this kind of visualization platform for NASA products, basically. Um, so the exercise that I was showing earlier is to visualize SO2 emission, for example, for the Taal 2020 eruption. We're going to use this to just, take a look at, well, look at the event. So if you're on your computer, you can just go to worldview.earthdata.nasa.gov, and then you'll see this platform, for example. So normally the default is that you have MODIS there, very cloudy, you can see. But if you want to go to a volcanic area, it's hard to see where it is. So I would always start by adding the S3 base map layer. We'll just put that there. And then you can see much more of the globe period. Okay, so we're going to the Philippines. And then we're going to Taal volcano, basically. Maybe I should zoom out a bit. And then what we want to do is that we want to add a layer. And then I will just search for SO2. For this, you have like several SO2 products, but for this case, we're just going to use the Aqua ARS data and then the Tropomi data. So these two data sets provides you SO2 information, but they operate on a different, they sense different things, basically. They are looking at the different slices of the atmosphere. Tropomi or Sentinel 5P can, it's total vertical column. I think it's more sensitive to from the ground to up to 15 kilometers. Whereas the ARS or the Aqua, you're seeing really most of the top of the atmosphere. And if there's an eruption, for example, it can help inform aviation if the plume reached the stratosphere. So, okay, and so I loaded those two data sets. If you're following me online, I'll just put this 2020. I know it happened in 2020 and January. I'll start with January 1, just to give you good animation of what happened. So I have turned on both the tropomy and then the aqua imageries here, and you can see that they are in Dobson units. So 1 DU is equal to 269 times 10 to the 16 molecules per square centimeters. It indicates the number of SO2 molecules in the atmosphere column per unit area, basically. But again, they're not sensing the same part of the atmosphere. So we can just go through it. January 1, the eruption happened January 12th. So wait for it. You can see blue is the tropomy, and then the other color is from the aqua data. So that's January 12th. You can see if I turn the tropomy off for a bit, you can see that is the range of the SO2 detected by the satellite, and then went away quickly, of course, the next day. And so Aqua has like daily acquisition, if I'm not mistaken. And then if we just turn this on, again, just turn off this one so we're not confused, you can see, and if I go back a bit, the tropomy data would show you this kind of information. So note that as we know, SO2 are very hazardous to health. I think the healthy threshold is supposed to be less than 1 DU, and if tropomy is sensing something, let's go back 13 here, really, at 24 DU or somewhere here, 32, if you're in this region, it's very hazardous for the health. So it's this satellite information helps us inform about health decision makers, plan for their for example um, uh, constituents or people who can be directly affected by this event. Okay, any questions so far? Okay, no questions.
Nope. So far, there's nothing.
Okay, so if I come back here to my slide, okay, that's the thing that you could just use and see, and you can download those data afterwards. Depends, and you can use them for further analysis. Yeah, so that's just like an example of what you can do with optical data and how you could use it for volcano monitoring, tracking SO2 emission in space. But now I'll push towards the radar data sets or products. So radar is literally a complex product. If you load the radar data, there are 2 components that you could get from it. It's not just an image. So when you load an optical data, you see like several bands, right? They're in different bands and spectrums, and you see just gray things. But radar data is not like that. It's a complex signal. Once you load them, you have to separate the amplitude component from the phase component. And here on the left, you can see what we see as the amplitude. And on the right, you can see the phase. So the amplitude is basically the backscattered energy of the emitted wave. But if you just look at the phase component of one radar data, it's just like nothing. It's just noise and stuff. But we will go back to this concept of like leveraging or using the phase to measure ground deformation later on. In terms of this of the backscatter image, what we can do is are many applications that you can do on the amplitude part. So radar is again an active system, and it sends you this microwave pulses, and then the measured pulse comes back and allows you to observe uh, the Earth or your site of interest. From that return signal, things like surface roughness, moisture, and structure can be inferred. And then if you basically think of using a radar to form an image, we call it synthetic aperture radar in this case because um, in space, you have to consider two things when you're deploying things in space. You have to think about the resolution of the image that you would receive later on. Um, and in order for a radar to form an image, there are two directions that you need to consider. One is the cross track of what is called controlled basically by the timing of the radar pulses, and then the along track, which is controlled by the size of the antenna. And this would lead to this fundamental limitation of how you could get high resolution information in the along track direction, or where, the path of the satellite. Um, and that would require really large antenna, but you cannot deploy large antenna in space in like hundreds of, orders of meters. It's just not practical and, nearly, well, impossible. So, in terms of like satellite systems, there is this system called SAR, synthetic aperture radar, that you often would hear. It's a clever solution where the satellite moves along its orbit, and then it sends multiple radar pulses over this same target from slightly different positions, and then combine them to effectively simulate the large antenna. So that's why you would hear it's a synthetic aperture, because basically you are recreating or simulating the large antenna from the motion of the satellite. And that will help you achieve or want to achieve to get a high spatial resolution from a very, relatively small system. So in this slide, I'm showing that radar can be emitted and received in two different or many different here horizontal and vertical directions. So you can have different polarization combinations such as HH, HV, VV, and VH. It just means that H, first one is the transmitted wave, and if it's received vertically, then that will be an HV. If they are both transmitted and received in a horizontal polarization, then you will have an HH kind of uh, um, flag in your image. But what's important here is that this combination of copolarized, what we call copolarized, when you have both HH or VV transmitted and received, and analyzing it with copolarized data sets, is that it can give you the characteristic of the ground, such as surface roughness, vegetation, and other structural features. And an application of this, for example, is in volcanic flow mapping. Here, this is from Rogic et al. 2023. This is an airborne SAR amplitude data. You can see again, it's just speckly, black and white image. But if you combine it with, combine different polarization and use red, for example, as VV, red band as VV, and colorize the green as VH, and the ratio as, for example, the blue band, then you can have something like this. Or this one, they use a different color. And if you do some more statistics and for example, in statistics or statistical analysis on the spatial image, you move a moving window or averaging, you could obtain something like this. Basically, you average some of the pixels, and then you sort of average information here, and it can help you distinguish deposits, delineate deposits or map deposits. In this case, I think the application was this is a debris avalanche deposit, and then this one around here, or this greenish here, were lahar flows. Yeah, so these are a couple of applications where you could use the backscatter data from radar in terms of volcanic applications. I have this demo here for RTC using Opera data, but I don't think we have time to run through the IPython notebook at this point. But what I'm sort of just thinking is that since RTC, not every RTC data that we provide under Opera is in Worldview, could just go through Worldview basically and have a look at some of the examples where you could use lava flow. Again, I'm gonna go to Worldview and then just gonna remove this data sets here, for example, and instead I will add RTC. So if I get RTC data here, can have that. Okay, was it added? Okay, it was added. Okay, it's in there, and then I will just go. In this case, I'm interested in looking at the eruption in Krashenikov last year after the large earthquake event in Kamchatka. So this is a volcano I'm interested at. If I go to the eruption, around the eruption period, let's say it was 2025, it was July, and then go 30, I think it's August 1 last year. Okay, can see something like this. So you see highlights the flow there, can actually turn this off and on, and you can actually delineate the flow, old flows nicely. And then an eruption happened on August 2 UTC, August 3, I think, in local time in Kamchatka, but you don't have radar data yet. That period, there wasn't an acquisition. So Sentinel-1 data, the RTC data that we are providing is from Sentinel-1. So there's a repeat period of between 6 to 12 days. Okay, there isn't. So on August 5, we have a data. We just zoom in. And if you want to actually compare layers or do a comparison window, you can also do that. I will just put this one as, this is my August 5, basically. And then I will use A as my August 1. Okay, so you have no eruption yet, and then after the eruption, you see that kind of flow. And then there's another acquisition the day after, for example, August 5. If I just go to B and then run that, you can see a very good growth of the lava flow in this case. And of course, I don't know if there is like data after, but I think there was another one in September 18 of 17. So you can compare that, and then you can see basically compare again with A, which is August 6 or August 5, and how much the lava flow grew basically towards the end of the eruption. So this is something that that you can do with just looking at available RTC data and just playing with Worldview platform provided by NASA.
Great. Can you briefly explain what RTC means?
So RTC, yeah, it was supposed to be part of the exercise, but Yeah, so it's a radiometrically and terrain corrected data set. If I go to my slide again here, so once you load an RTC data, a backscatter data, you for Opera you will have the gamma naught in basic term, or I mean the default product that is provided. It's brightness corrected. It looks like this. For example, it's typically used for flood monitoring or flood delineation. And it's also terrain corrected. That's why you see that it's almost flat. So the beta naught, it's just brightness corrected and you still see the terrains there or the topography. Sigma naught is just reflecting you the local terrain and it's also corrected for brightness. So that's the difference between gamma naught and sigma naught. But it's an amplitude data that you basically, yeah, just to colorize it in my language is that you load different polarizations into or assign the different assign the different polarizations into different colors. So VV to red and H to VH to green, and then the ratio of them for the blue band, and you can have something like this, and it will give you, really striking features of mapping several system or several flows, for example, in our case. Okay, so you can move towards INSAR. I want to really be able to go through showing you how we could use NISAR data. So for this case, going back to this image here or that I have earlier, so you have the amplitude component and again the phase component. So these are images taken over Taal in the Philippines. This is where the Taal volcano is. You see that it's somehow flipped because of the orientation or when this data was actually obtained or acquired. It's in the descending track. That's why it looks like that. And if you look at the phase component, again, it's noisy. It doesn't have any meaning at this point. But if you take another one image or another phase data on another date, and there happen to be a large deformation event that happened in between these two scenes or two dates, then you can obtain and you cross multiply or get the difference of the phases. Basically, in mathematical terms, when you get the differential phase, you just cross multiply these two phase components. You will obtain something like this. So you'll be able to get the displacement of the ground as a result of the January 12 eruption over Taal. You can see it's a really big eruption. The denser the fringe, the more ground movement basically had occurred. And in this case, this was from Sentinel-1, and the wavelength, meaning I always think of the wavelength as the rulers or the length of the ruler that you can use to measure the deformation or the ground displacement. So in this case, you can measure only up to 2.8 or half of the wavelength of the satellite, which is 2.8 centimeters. And then after that, it saturates and you wrap the phase. That's why you get another fringe signal, basically. So if you count all the fringe, that's the maximum amount of ground deformation that you get, especially on the near field. But with radar, it saturates a lot because it can only give you up to 2.8 centimeter of ground measurement. If you go to longer wavelengths like L-band, you have 12 cm. So basically, you can see less fringes, but you can still measure the same amount of deformation just less dense fringes because you're using a longer wavelength sensor. We'll show you later how that would look like basically. But so when we think of the interferometric phase or interferometric phase difference, it's actually not just the deformation that's in it. In this case, the dominant signal is just the deformation because we know there's a huge, ground movement as a result of the eruption. But here, basically, the differential phase is composed of the orbital term, which comes from the satellite's an orbit uncertainty, and tiny errors in the satellite position can introduce some phase ramps across the image. There's the topographic term, phase topo, in that equation there, and it's related to the topography or the elevation of the terrain. If you don't perfectly remove the topographic phase using a digital elevation model, then you can have a residual topography that can show up in your interferogram. It's not entirely bad at all sometimes, because sometimes you want to use the phase topo information when you want to get the thickness of the flows, for example, or the lava flows after an eruption or when an eruption is occurring. This term here, the phase ATM, this is the atmospheric term, and its contribution from the atmosphere, mainly due to water vapor pressure differences between acquisitions. It can introduce spatially correlated signals that can actually sometimes look like deformation, especially on volcanoes. It's sometimes very tricky to look at volcanic signals, because atmosphere can mimic the topography, and you will have fringe like signals that you would think that they are deformation, but they are actually atmosphere. So sometimes it's necessary it takes an expert to look at the atmospheric signal, and also it's necessary to look at different data interferograms acquiring the same kind of event. The other signal is the phase noise. This kind of light includes some other noise signal, the correlation, thermal noise, processing errors that you have in your interferogram. And of course, what we are always interested are this term here, which is our deformation term. It represents the change in the distance between the satellite and the ground along the line of sight, and can be scaled by the radar wavelength, as I already explained earlier. And the last one is the phase ambiguity here, and 2 pi. This is modulo 2 pi, and again, it's because of the limitation of the wavelength when it wraps every cycle. So we only observe phase within a limited range, and we need to actually unwrap the phase so that we would have or recover the true displacement of the ground in, say, meters unit, and not in wrapped phase or counting fringes way, basically. So in radar,
there's a question in the chat. Well, 2 questions. One is about, is it possible to find the lava flow change in volume and up to how much thickness we can detect? And the second question is the RTC Opera data available worldwide?
Yes, the RTC data from Opera is available worldwide in 30-meter resolution. For the first question about thickness, can you repeat it again, Sylvain?
Yeah, it's basically, can you calculate lava flow volumes from this data using INSAR? I guess that's what the question is. So can you calculate volume of lava flows using INSAR, and how much thickness it can detect? So getting
So it
based on the
depends
satellites,
on the
right?
satellite
Yeah.
system, I would say. But the key thing to do that is that you have to have the separation of. So this is a repeat pass system. Basically, you have an AOI, you have a volcano, and then the satellite comes back to it every once in a while and take acquisition at that, roughly exact location. But in terms of deformation, what we want, for example, if the focus is deformation, is a small separation on the, separation between those satellites, because we want to have to obtain really precise measurement of how much the ground moved. But when it comes to topography, you want to be able to acquire radar data almost at the same time and with a large separation, so you can basically look at the thickness of the flow. It's a different application, but it's doable with large baseline of the satellites. I would say it's not part of the INSAR. This kind of like you just have two data sets and then you want to get the thickness of the flow. You need to get more or dive more into the analysis just to retrieve this topographic base. I removed this. I removed it in my slide, but let me just show it for example related to that question before I move to INSOR. But so here is an example of that where you can acquire the east-west, the displacement rate, the vertical displacement rate, and the thickness map. And this is using high resolution radar data. It's not freely available to everyone. It's a Cosmos Skymed data that we utilize here. But you basically stack the images together, and what we're looking at is not really the co-eruptive data, but post-eruptive emplacement already of the flow, and then we stack the data together and do an inversion using several imageries and several viewing geometries of the satellite. That you could really get this thickness map and also the displacement rate. Okay. I have 15 minutes left, but I really want us to go and really be able to try nicer data. So going back to this slide here, again, in radar interferometry, if you're interested in deformation, you try to remove in as much as possible all these other phase contributions, and you keep this one. Sometimes you want to keep this, like the question earlier, but yeah. So this is one of the example for like showing what an L-band data can look like and a C-band can look like, and then capturing the same kind of event. So this is again Krasheninnikov volcano in Kamchatka, Russia. I had an eruption in August 2, UTC, again August 3 local time there. But you can see here, this is more coherent data on L-band. That's one difference. You can see something like much more noisier in this case. The ALOS data, it's not regularly acquired at all parts of the world. So there's no like 12-day acquisition nowadays. For example, when you compare it with Sentinel-1, that's why here we have like almost a year of temporal baseline, but it's still capturing basically the event here. You can see that you have really the less amount of fringes that kind of like uh, how do you say this, kind of like becomes like this or saturated. I'm looking for the word saturated. It becomes saturated because it has a longer wavelength. You can see for Sentinel-1 data here at C-band, it's capturing the same event, August 3, although this one is already in the fifth, so there's more cumulative displacement that had occurred here. Basically, the lava flow kind of possibly have emplaced already in this northern region, but you can see that though in this part of the, especially here, you have a lot of fringes that have already saturated. That's because it's a C-band. Okay, we will go back to this as an exercise, but when you read an interferogram, the important thing to keep in mind is what is the acquisition date that is covered by the interferogram, and then what is the radar wavelength. If it's C-band, it's 5.6 roughly for Sentinel-1. One fringe is equivalent to half the wavelength of the satellite, which is 2.8. And then for L-band, for NISAR specifically, it's 24 centimeters of wavelength. And then, of course, the half of the wavelength is 12 cm in terms of change. So, and the second thing is how much these fringes occur, and you would count from the outer edge to basically the center, and you multiply it by half of the wavelength of satellite. So for here, for example, if I just count here, I will just count like 1, 2, 3, and then yeah, maybe half. And then the direction or the color scale that is provided. Here there wasn't a color scale, but later we will see um, if it's going from blue to green to yellow to red, and then the orientation of it, it tells you if the ground is moving towards the satellite or away from the satellite.
So in the next slides, I will show you how to download, load, and interpret data from NISAR. We will take the Erta Alia Diking event that occurred in November 2025, just after the eruption of Haile Gubi in Africa. So to download the NISAR data, we will use ASF Vertex. So we'll go ahead and go to our favorite browser and just type in search.asf.alaska.edu. So we're interested in Erta Alia, which is in Africa. So we'll draw a bounding box, for example, to search data. I'll just draw that. And then I will choose NISAR as our data set and then click search. So you will notice that we have plenty of data sets available, various products over this region. But for this demonstration, we're only interested for the GONW or the geocoded unwrapped interferogram. So we will go and click filter and then just filter the GONW product from the science product tab. We'll just click that and then click on search here. And then these are all the GONW products made available for this region when they release the uncalibrated sample products. So we're interested on the dates between November 2022 and December 4. So I have already pre-downloaded these data sets. We'll go ahead and search or load them via QGIS. But if you want to download these products, just highlight the data you want to download and just click this icon here. So I'm going to now go to QGIS and let's visualize the product. But before that, so there are two things we want to load or visualize: the wrap phase and the unwrap phase. To load the wrap phase, it's a complex product, so we need a driver for that. So you need this. Oops, you need to remember this script. Derived underscore sub data set. Then you want to load the phase and then the netcdf file, your data path where your downloaded product lives, and the file name and this data layer. So we will go to QGIS and just load that. Click on layer, add raster layer. So you see here, we'll just type that path that I showed you earlier in this tab. Again, derive underscore subdata set. You want to load the face, and then it's a netcdf file, and then you just copy the file name and the data layer. The wrap phrase is what you're interested for this case, so just hit add here, and there you go. The data is loaded. If you want to change the color, double click on this layer. Click create the render type. I am interested in single band pseudo color, and you can choose from different color maps available here in QGIS. I have my own color that I like, so I have the jet one, and I will just load it, and I will just hit apply, and there you go. You have successfully loaded the NISAR wrap phase layer. Now we want to load the unwrap one as well, and just go to the same add layer tab. So instead of like having a driver to load the face, we don't need that anymore. So we will just delete these and then just keep the netcdf file. However, you want to load a different layer. I have it in the slide deck that I've showed earlier. So if you want to load the unwrap phase, this is the script that you wanted. You want the unwrapped interferogram and the unwrapped phase. Okay, if we go back to QGIS. Oops. Here, so we want the unwrapped interferogram and then the unwrapped face layer. Okay, let's see if that works. Okay, that works. And similarly, if you want to change the color, you can just go and click single band pseudo color, and you can just click apply, and basically that is your unwrap face. And you can inspect it, check the data. Yeah, and then that's pretty much it for downloading and visualizing the product or the nicer product using QGIS. Now, when it comes to interpretation, let's go back to this slide deck here. There are three things that we need to consider. First is when and what are what are the image dates and the radar wavelength. For example, we are looking at nicer products this time, so it's an L band. The wavelength is 24 centimeters. So one fringe is half of the wavelength. That is 12 centimeters in change for each fringe. For C-band, for Sentinel-1, the wavelength is 5.6 centimeters. And so half of the wavelength, meaning each each fringe here means that there is a change or a movement of 2.8 centimeters for C-band. Now, the second thing you have to consider is how many are the concentric colors that you can count from the outer edge to the center, and then you have to multiply it by half of the wavelengths to know how much the ground moved. The third and the most important one is also to be able to know what is the motion of the ground. You have to use the color scale. If it's moving here from red to blue, it means for this specific diagram, it's movement away from satellite. And then if it's blue to red, in this case, you have movement towards the satellite. So for Airtalia, we'll go ahead and try to interpret that. So we have this wrap face here. We'll first check when are the dates, what are our reference dates and secondary dates. So our reference date is 2025, 11/2022, November 2022 of 2025, and our secondary date is December 4, 2025. So we're looking at how much the ground moved between these two dates. The track is ascending, and it's provided by this in this file name here. And NISAR data or NISAR products are in left looking mode. So the satellite is moving here, but the flight track of the satellite is moving from south to north, and it's looking left. So color scale for the wrap phase, from blue, if the color change from outer to center, change from blue to green to yellow to red, that means that the ground is moving away from the satellite. Basically, the distance between the satellite and the ground has increased. That's what we call as the range increase. And if it's moving from red to yellow to green to blue, then that means that there is a decrease in the satellite and the ground distance. That means that the range had decreased. So in this case, if we count how many fringes on this side of the dike, we have we can count 1, 2, 3, 4, around 5 concentric fringes, and then we'll check the color. The color is from let's start here. So blue, green, yellow, and then red. So from blue to green to yellow to red, what that means we are the ground. This part of the ground is moving away from the satellite. The range increases. Whereas in this side, we have just one concentric fringe, and we can see that the color pattern is from red, uh, from red, oops, from red to yellow, to green, and uh, we don't see the blue here, but basically the pattern is from red, yellow, green to blue, and that means that we are in the range decrease side where this ground moves toward the satellite. And you can confirm it in this line of sight displacement. Basically, if you convert this wrap phase into to metric units by just unwrapping the face, you will see that there is a negative value here, which means that the ground moved away from the satellite, and here the ground moves toward the satellite. And yeah, basically that's it. Congratulations, you have successfully read and interpreted the co-eruptive data.
I just want to quickly show you some of these things. It's very fundamental kind of processing I know and presentation, but here you've already loaded and supposedly know now how to interpret and insert data. But of course, you want to have a time series later on, and you need stack of this data, and you need to process and recreate the time series. And it's a long process before you go and dive into the science of it and understanding of what really is going on your volcano of interest. So projects like Opera is making products or high-level products for you. We have several products that are available for ground deformation monitoring. We have the displacement, which is provided only in North America. It's in 30-meter resolution, and soon we will make a VLM, or really a decomposed vertical land and horizontal motion. So you don't need to understand what is the line of sight, where is the ascending and descending, what is the ascending and descending track. So it's more of like really an high level product or level for product that we call for our case. But again, it's just North America, and in our case, North America is everything within the U.S. mainland and U.S. territories, and 200 kilometers up of the U.S. border to Canada, and up to Panama or Central America down the U.S. mainland. These are the examples of what you can retrieve from the displacement Sentinel-1 products. This is reawakening of Mount Edgecombe volcano. You can see here that around in 2018, sudden inflation event happened. And to simplify your kind of like process, or if you just want to have a first look of what is like the deformation on your volcano of interest. For example, here I just went to Alaska, or that part is again Edgecombe, and I will just go there and just click here, and then you will have this kind of time series. So it gives you an understanding of what's happening in this volcano. And of course, we have again North America coverage here. As you can see, it's up to here in Panama, and you can just explore and dive into to this platform. It's displacement asfalaska.edu, where we have this visualization platform. There's a caveat though here. We're showing just this sort of short wavelength layer. Basically it's just purely for visualization. So if there's a caveat on it, there's an info that you can read here about those caveats, but basically the filter that we use, depending on how large the spatial extent of your ground deformation, it can affect the spatial features of the displacement. In the end, when we are talking about volcano monitoring and forecasting, we should go and inspect the nominal product and not this product here. This is again just serves as a visualization tool for everyone, as a first order check or inspection of what's going on in my house. For example, is it on top of the fault line for some people, and things like that. So with that, I'm going to end my presentation. We have several Python-based notebooks in our GitHub, and you can explore them as well. And more information to get you started with NASA datasets are in this slide, and I will make sure that Sylvan has this slide for you. And yeah, thank you very much, everyone.
Thanks, Grace. Not much time for questions, but I would like to add that if you have any question, yeah, okay, there's one. Just wanted to add that you can also look at some Jupyter notebooks on Victor about either the Opera products or generating interprograms from SLC data. They are all located in the shared folder. So if you go in the shared folder and then you go into workflows, remote sensing, and then there you will find about 7 or 8 notebooks about what Grace just talked about. So don't hesitate to open them, look at them, go through them, and then give us any comments or question you may have about that. It's still work in progress, so some of these notebooks are still evolving with time. So if you run into some issues, when you run them, don't hesitate to ask us if there's any trouble.
Yeah, we're gonna try and send some kind of like step-by-step exercise maybe. So stay tuned.
Cool.
Thank you, everyone.
Thank you, Grace. Yeah, so there was questions, right? Did someone have a question?
Thank you, Grace.
Yeah, and feel free to reach out to the Victor team or directly to me if you have questions and stuff.
All right. Thanks, everybody, and see you next week for the last class.
Bye. Bye.
Thanks, Grace. Bye.